Good morning, everybody, or good afternoon, depending where you are in the world. Welcome to the rollout training of the project DLT4ALL, which is actually an Erasmus project. Today, we will be actually discussing two of the modules that we're preparing, well, actually in this training session. Today, we will be discussing the decentralized applications, and tomorrow, the DAOs. Let me say, before we actually begin, that this session will be recorded. So please, if anybody has any objections, just write something on the chat room now. Okay, Valentino, can I share my screen, please? Valentino, I cannot share. Okay. All right, let me just enlarge the screen. Display. Okay, before we begin, please allow me to say a few words on the project itself. So as I have already mentioned, DLT4ALL, it's a project funded by the European Commission. It is an Erasmus Plus project. And the main aim of it is to address the lack of knowledge in terms of blockchain technologies and distributed ledgers. This is a project that is actually it's a project that we are 8 partners. The University of Nicosia is the coordinator of the whole project. The target audience is university students and researchers, entrepreneurs, high-tech SMEs, early-stage investors, incubators, and actually anybody who is interested in blockchain technologies. We are preparing 8 thematic priorities, 8 thematic modules ranging from peer-to-peer database design, encryption techniques, consensus algorithms, distributed autonomous organizations. And as I have already mentioned, the University of Nicosia is preparing the decentralized applications. So this is what we will be presenting today. I will skip some of this. It is both business-oriented and technical-oriented in the sense that we would like all these different modules to be applicable to people with a business background or with a technical background. We're organizing at this point in time 4 different test rollouts that are taking place in the participating countries, including besides Cyprus, Italy, Greece, and Spain. And the objective, our main objective for today is actually to obtain your feedback on how we can improve these modules before we actually launch them. The initial plan was that these different modules would be offered both online and face-to-face. Now, with the current situation that we have worldwide, we are just taking it day by day, even though this one was going to be face-to-face. Unfortunately, due to COVID, we cannot have this as a face-to-face. We're hoping that for the following ones, for the actual full academies, we will be able to have them face-to-face. In these different modules, there will be, of course, assignments and a final exam. The final exam will be given for those who want to have a certificate after they take all the modules. So, and upon, of course, the successful completion of the modules, the learner will be given a certificate that will be issued on the blockchain by the University of Nicosia. We will start now with the decentralized applications. The module, one of the two modules that the university here was responsible for preparing. And as we have said, it's going to be on decentralized applications. And I will pass the floor now to my colleague, Dr. Elias Iosif, to continue with the introductory of this session. Ilya?
Hello, everyone. Thank you so much. Excuse me, sorry.
You have to share your screen now.
I was saying welcome to all. I think for part one, topic one is my colleague Klitos presenting.
Okay.
So,
sorry. I should mention that actually this course here today will be delivered by two very good colleagues of mine, Elias Iosif and Klitos Christodoulou.
Hello, everybody. Welcome. Can you please pass the token to myself so that I can share my screen? Thank you. Great. Can you all see my screen? Hello. Hello. Can you all see my screen?
Yes, Lido, we can see it.
Perfect. So what we are aiming with Learning Module 7 is to provide an overview of decentralized applications. We will be covering some of the ideas, the implementation of some such applications at the high level, since the aim of this course is not to get into the very technical details, but to provide an abstraction and general conceptualization of the main ideas of building blockchain-based decentralized applications. And moving forward from this, we have all observed that this technology is disrupting many industries, and therefore we have now a new technological stack available for developers for implementing such blockchain-based decentralized applications. So actually, an overview of this course will be to provide a high-level anatomy of the apps. That means what is the technologies that we can use in order to implement such decentralized applications and design such decentralized applications. Of course, the aim of this first session is to get the basics and add the fundamentals with regards to how to build such applications. And our aim here is to, since this learning module is a continuation of the courses that are provided within the DLT4ALL European program, it needs to come as a whole, and therefore at the beginning we will be reminding people of some of the underlying terminologies with regards to decentralized applications. Decentralized applications, of course, are consisting of two parts. there is the front end, which is usually the user interface, a web-based application or mobile application. And then we have the middle layer, which is the interface that connects the front end with the back end, and of course the back end, which is consisting of a set of smart contracts. So the first terminology, the first definition that we need to be clear at is what is a smart contract, and how are these smart contracts supporting the infrastructure for implementing decentralized applications. So at the beginning, we set the foundations, components also that consist a blockchain system. At the abstract level, we have of course, the node, which is the underlying layer that supports the peer-to-peer network. And of course, there is the shared ledger, which is the data structure, which is replicated to each node. Which is actually the rules that all participants need to adhere to. And of course, the protocol defines also other characteristics of the network, such as the right of the nodes, the consensus mechanism used, how blocks are signed, and etc. And the incentivization structures are also embedded in these types of networks. Since a blockchain system consists of several parts, we tend to classify them into various layers. As I previously mentioned, at the very last layer, we have the infrastructure, which is the underlying layer, the actual hardware that hosts the network itself, the nodes. This is where the primitive information is stored, the ledger, and all the information with regards to the keys, to the cryptography required, etc. And also, this is where the miners are doing the work, or the validators are signing the blocks, etc. for the progression of the blockchain, and etc. At the upper layer, we have the network layer, which is all the mechanisms that are used for the communication and the message passing between the nodes. So this defines, in essence, the topology of the network. Usually, this consists of a gossip protocol that transfers the messages from one node to another, and make sure that at some point after the consensus is taking place, there is agreement to the entire network, making sure that all the participants are looking at the same state of the world. And moving from there, at the top layer, we have also the consensus and also the applications that are consisting part also of the network. Okay, so the application layer is at the top, and there is actually the way that the users, the clients, are actually interacting with the platform, with the protocol. So we have the APIs that also provide some functionality at the user level, and the interfaces that passes that messages, that invocation of functions and methods to the decentralized protocol. Another layer which is also important in such decentralized protocols to consider, despite the smart contracts and the data store, as we described previously, is the interoperability with other chains. And this is where the idea of side chains come into place. These are layers built on top of the blockchain infrastructure layer. So again, a summary of all the layers. And moving from here, we have the definition of what's in the app. Okay, and as I mentioned previously, the app consists of a set of smart contracts at the back end and a user interface at the front end, which provides the interactivity of the application to the end user. Everything is sustained upon a peer-to-peer protocol, and the code that is executed as part of the smart contracts is in essence self-executed, since once the code is deployed, the smart contracts run actually forever, since the network is maintained on a set of distributed peer-to-peer nodes. So, what does it mean for an application to be qualified as a decentralized application? Actually, in the ecosystem in general, it's not enough just to have an application with a front end and a back end that is maintained with a couple of smart contracts. So for a decentralized application to be considered fully decentralized, then it needs to meet some certain criteria that are set by the ecosystem. Okay, so it needs to be open source first of all. Okay, so we cannot say that a commercial application which is on some proprietary network it's hit the is considered fully decentralized. Okay, it could be decentralized if it is supported by a peer-to-peer network, but the degree of decentralization varies according to the following criteria. So it needs to be open source, it needs to be open to the public. It may also incorporate a digital currency, a native digital currency that incentivizes participation to the application. Okay, it needs to be powered by an agreement mechanism. Therefore, it needs to be on a protocol that agreement comes after consensus. Next, since this is a decentralized application, as we previously highlighted, needs to be executed on a set of smart contracts that are validated upon the blockchain protocol. And lastly, it needs to be, as we highlighted previously, decentralized, meaning that there is not some central point of failure for the entire application, meaning that reliability is ensured, even in the case that some nodes are not supporting at that particular time the network in general. This is the power of decentralized blockchain networks. And moving from traditional web applications development, we've seen that the inception of this new idea of Web 3.0 and the decentralization and the trust that is built upon blockchain protocols, we are observing a paradigm shift from how developers are building traditional Web 2.0 applications and versus how decentralized applications sustained by distributed ledgers are actually implemented. And there we're considering various dimensions. So once we design an application, we need to consider where the computation of the application is taking place. Traditionally, this computation, especially for cases of web applications, it takes place to an Amazon, let's say, cloud or any cloud service. It's scalable depending on the machines, and of course, cloud services provide scalability. And the storage is also on the cloud. Okay, everything is centralized in essence. With regards to connectivity with other applications, we have interactions between third-party application interfaces, and the monetization structures for these applications is usually the classical advertisement system, and the payments, of course, are supported with the traditional ways of us doing payments on the digital world. Okay, using our Visa, electronic money via PayPal, etc. But is this enough? And the answer is that with the emergence of blockchain technology, we are now in a paradigm shift where we have some alternatives and we have some very good alternatives with key characteristics and properties that we haven't seen before. Okay, so now we can build our applications with the use of smart contracts. We can deploy them on a peer-to-peer blockchain protocol, such as, for example, Ethereum, the mainnet Ethereum, and run our smart contracts on the Ethereum virtual machine. There is scalability. We've seen how this blockchain trilemma, it's moving various protocols into the next evolution stage, and there is work in with regards to the scalability of such networks. With regards to storage, we have many alternatives now. So we are, as I've said, we are in a paradigm shift. So we are moving the responsibility and the ownership of the data back to the user, meaning that we have decentralized peer-to-peer storages that the user can use. And of course, the user has the ownership of data. To the real world, we have oracles that allows us to connect to the real world and read data back to the blockchain world so that we can take decisions or change the state of our contracts. And we have various tokenization models. Okay, we have various tokenization models and opportunities for monetization and ownership of codes. And with regards to payments, lastly, digital currencies, cryptocurrencies are used for all the settlement of payments in such decentralized applications. So there is also a classification on how much decentralization, how much decentralized an application is. So we have 3 classifications here. And with this centralization, we have certain benefits, as I mentioned previously. We have automation. We have smart contracts that are self-executable codes. Okay. We have transparency. So everything is recorded on a immutable ledger. So it's both secure and transparent the same way. We have also a certain degree of privacy with pseudonymous accounts and the use of cryptography. And we have also models of governance. Okay, and this is where this concept of decentralized. Also, we've seen how the authorities and the governance of the networks could also be more autonomous and more democratic in a sense, with incentivizing the participation of other actors as well. And of course, we have open source code, fault tolerance, which is of course provided by the mechanisms that support the peer-to-peer network. And incentivization structures in the form of native cryptocurrencies that are used by the network or to incentivize the participation to some decentralized application. Also, we have seen cases where these digital cryptocurrencies are also being used by incentivizing other programmers, other communities into identifying potential bugs that are that could be exist in a smart contract, and also other improvements of existing contracts. And we've seen various proposals for implementation of decentralized applications, and of course the first decentralized application was Bitcoin. So we are just mentioning here for historical purposes. I think that's the first part with regards to the introduction, and I will be passing the floor to my colleague Elias for referring to some design patterns that could be used for decentralized applications.
Thank you, Clito. So I think it's time to be the presenter. Can you see my shared screen?
Yes, we can see it.
So, as my colleague Litos have mentioned, the general idea is that the main characteristic of the family, the broad family of decentralized applications, is the ability, from speaking from a technical point of view, to move forward the very first decentralized application, which is, of course, the ability to conduct digital payments according to the principles and properties of blockchain. Of course, the specific example of this first application is Bitcoin-based transaction. However, things are changing. Things in terms of flexibility are becoming more interesting. Now we have the ability to develop more complex and more interesting applications using the expressive power, if you like, the expressivity of smart contracts. So this is software engineering, among other things. This is a software engineering business where a key role is assigned to software engineers, software analysts, software architects, software security experts, auditors, etc., etc. So this is a digital game, and digital systems start in, or include, if you like, the design phase. This part here, topic number 2, is to present the overall idea of having the design phase as a major phase of your approach, your solution, illustrate some high-level and commonly used design patterns, and of course, we may have a short discussion. Feel free to interrupt me at any point, or if you think better, you may save your questions for the end of this part. So we're going to quickly introduce this topic and see a number of relevant and indicative examples spanning from the interaction with the external world, how to handle and manage data, up to some structural patterns. Okay, from a software engineering point of view, design patterns refer to a solution that applies to a common problem within the framework of software engineering. Some key elements are processors, connectors, and the data itself. So design patterns define the interaction and the restrictions that hold between those elements. Design patterns can be thought as a guideline and generic guideline meant for software architects during the process of designing and building decentralized blockchain-based applications. So in this part, we will cover the 4 common types of design patterns dealing with the communication with the external world, based on the fact that a blockchain system, a blockchain as a data structure is isolated from the external world. We will present data management patterns, security patterns, as well as contract structural patterns. For each pattern, we thought it useful to encode its presentation, its description with respect to a number of fields. So we have utilized the following structure. Each pattern is more or less defined with regards to a brief description, the description of the context in which this pattern is instantiated, the definition of the problem of interest, the description of the challenges along with some suggested solutions that are feasible, and where applicable, some related examples will be provided. So before going into the specific details of decentralized design patterns, I would like to ask if there are any questions regarding what design pattern means for the case of dApps. Is everything clear? Any question? No. Thank you, Michael. So communication with the external world. As my colleague we have the concept of oracles. Of course, this is not the traditional, the typical meaning of oracle. Traditionally, oracle refers to an entity who has somehow supernatural capabilities regarding the prediction of the future. Here is something, the meaning is something different, but let's see first of all the description. So the essence here is how to embed the states of an external system into the environment of a blockchain, which is by definition closed. Each blockchain is isolated from any external system and resource. And given that we don't have so far any question, let me ask a question, and I would like to hear your opinion. Do you believe that this isolation, having the blockchain system as a data structure at the core of the blockchain, being isolated from the external systems and resources, do you believe that this property is a good one or a bad one? Do you consider this as an advantage or as a disadvantage? What's your view? Yes, I'm not seeing any responses so far. It seems that this question requires a bit of thinking. Things are not black and white. So let's make it's too early to comment by which perspective. For some reason, I can see the questions as they appear on the fly, trying to see how I can access them. So any Mm-hmm. So yes, I found it. So Andreas is saying that this is a beneficial feature in terms of security, but not convenient for exchanging information. Disadvantage. Mm-hmm. So I think I'm seeing a diverse set of opinions. So I think all of them are in general valid and correct, meaning that it depends on the use case. So just to give you my very own opinion is yes, in terms of security and similar things, this is what we need. However, this isolation makes things really difficult when we consider a blockchain-based system as a computational element within the context of a more complex, let's say, information system. It is likely that, in my opinion, it's very, very rare to have purely blockchain-based implementation, more or less at numerous points over your technology stack. You may need to incorporate other computational elements, so this limitation is probably will probably arise. So there is no clear answer here. Let me go back to the slide and try to put this problem into a more solid context. So let's define a blockchain-based computational component with the letter B, which can be thought as a component within a larger system denoted by the letter S. In this context, B, the blockchain-based system, needs to communicate with the constituent components of the larger system. So the smart contracts need to run. However, they cannot access the REST components of B. So the challenges is the isolation, the connectivity, and the availability of data. The solution deals with the utilization of oracles, which enable the evaluation of the conditions, the rules, if you like, the evaluation of certain, let's say, requirements that not can be encoded by smart contracts. We may have two general approaches. The first one is the Oracle is implemented as a smart contract, and its external states are being updated periodically, while in a second implementation paradigm, the Oracle is an off-chain server which requires permissions in order to sign blockchain transactions. Augur and Gnosis are two, I would say, indicative examples of this of a system that utilizes such oracles. Both of them fall under the prediction market use cases. Before proceeding to the next pattern, I would like to ask if there are any vague points here, questions or anything, or comments. Okay, but let me say that feel free to interrupt me at any point. The next design pattern is the encryption of on-chain data. Clearly, this is very, very interesting and important paradigm. Since we have the recent GDPR rules, we have seen very recently the COVID-19 situation and the need for exchanging accurate data. And these are only two of the data-related use cases. And when data are connected with physical entities, certain degree of security, meaning encryption, should be in place. So the overall description is how to preserve the confidentiality of blockchain stored data through encryption. The context is of this pattern is that some application should run on public blockchain. However, not all entities that participate in this public blockchain should be allowed to have unlimited access, especially to sensitive data. The problem is that by definition on public blockchains, anyone can join the network and gaining this way access to the data. This is, let's say, the default configuration. And regarding private-owned consortium blockchains, the network members are restricted by the controls that are included in the consortium, let's say, agreement, which is, of course, implemented in practice through smart contracts. However, all historical transactions are accessible to all members. I'm seeing a comment back by Andreas. Okay. Thanks. So the challenges here is the transparency. In some cases, we do not want full transparency, and the confidentiality of the sensitive data. So that is, we need to avoid the storage of such data in non-encrypted format. Obviously, the solution is the encryption of data prior. This is the key phrase here, prior to the on-chain storage. Another approach is the storage on an encrypted blockchain. This is okay, quite generic, but I mean, encrypted blockchain can mean many things. The basic idea is that you are in contrast to the encryption prior the on-chain storage. That is the first bullet above. The idea is to do not encrypt the data per se on the blockchain. However, you are building a surrounding encryption mechanism around those data. And the other approach that can be combined with the previous two is to distribute the encryption key only to specific network members. Now, those approaches introduce some, let's say, technical complexity, which may need off-chain key management, which is by itself probably not the 100% secure solution for handling these challenges. The next thing, next design pattern. Again, let me quickly remind that design patterns mean you can think of them as templates that can be used as generic guidelines for solving families of problems, especially during the design of blockchain-based application, the design of dApps. So the third example has to do with the enhancement of the securities of transactions that require multiple addresses. And let us give more information by defining the context of this pattern. So for some monetary blockchain-based applications, some types of transactions may need the approval of multiple addresses, multiple entities. For example, in the context of a healthcare system, you may assume multiple experts, multiple doctors, simply doctors that need to access the same medical record for reviewing, discussing, and agreeing on a joint action. So we need to asynchronously coordinate the authorization of those different addresses that, as said, correspond to different entities. The challenges is that we have minimum security. The requirement for flexibility is at the same time a challenge that is correlated with correlation. I think that is a simple mechanism that is available in many major blockchain implementations, including Bitcoin, is powerful here. It's the so-called M of N multi-signature mechanism, where M out of N private keys are needed for signing a transaction. A possible drawback, which is, I think, of minor nature, is that the potential signatories should be known in advance. However, I think this is not something major. My very personal view is that the multi-sig transactions is a simple to understand feature. Seems simple, however, enables very interesting use cases, like the healthcare related one just described. A pattern that is, I would say, close to the traditional notion of templates, macros used in the area of software engineering. Has to do with the creation, instantiation, to put it more accurately, on template contracts which live on chain. So here we may have an application which needs to utilize many instances that are derived from a base contract. Different instances enable, of course, a degree of customization. And an example is that different business processes can be encoded in different instances. The problem is that the off-chain maintenance of the contract does not enable consistency between the different instances. Imagine a business which consists of several departments which follow the same generic, let's say, process with regards to a target, with regards to a specified KPI. However, different departments may have slightly different privileges, etc. So the idea is to derive the base functionality from a base contract and let the differences be encoded into the contracts that are derived from this base contract. Of course, if you are coming from the software engineering world, you can instantly recognize the idea of inheritance. So, however, this is very, very useful is in many cases. And let me go directly to the probably one of the most indicative examples, to the Open Zeppelin, which is a library of reusable, and please pay attention to this word, safe smart contracts for the Ethereum blockchain. The notion of safety is of paramount importance. Let me put it simply. For the vast majority of cases, it is better to reuse, to inherit a smart contract, to inherit a property, to inherit a functionality from a base smart contract, like the contracts provided through Open Zeppelin, rather than trying to reinvent the wheel and implement it from scratch. This way, you have a very, very high probabilities to reuse a safe smart contracts, because the contracts provided through repositories like Open Zeppelin have gone through a detailed audit process. So this is the basic idea here. This design pattern is, as I was saying, closer to the implementation dimension of this set of patterns, but it is an important one, and that's why we think it is very useful to be aware of it. And just for the sake of completeness, let us also mention that at the end of each learning module, at the end of each section topic of this learning module, our plans is to provide a small set of multiple choice questions like these ones. For example, oracles can be utilized for the following task. Quite obvious, I think, is the answer, etc. And where this topic concludes with basic reference. This is a relatively recent book, Architecture for Blockchain Applications. The material presented in topic number 2 corresponds to chapter 7. I highly recommend this book. It's not deeply technical. I think covers a fair combination of technical as well as business background. This was published by Springer, a well-respected publishing house, and of course some few optional references. Yes, I agree with Natalia's comment, and that's why the off-chain storage is very, very frequently used, and the challenge is how to synchronize the two off-chain and on-chain operations in a way that the key properties of blockchains, starting from decentralization, should be preserved. Yes, I think we are ready to take any questions about topic number 2, design patterns. Otherwise, if there are no questions, we may proceed to the next topic.
Okay, thank you, Ilya. So, can you please provide me with the token so that I can resume the session? Okay. Can you hear me? Okay. So, following from topic 2, as Elias mentioned, part of all of the sessions currently presented are part of learning module number 7. Moving from design patterns, the module is also concerned with guidelines on the basic development of decentralized applications. As with all implementation, we need to start from the design. So first of all, the first step is to identify the problem in hand, to understand the domain and the current business logic that we would like to implement. What are the objectives for this decentralized application, and what will be the scope with regards to the users, etc. And there, we're moving to system analysis, which is to understand the requirements in detail and decide upon the software engineering model that we will be using in order to design our decentralized application. Usually, we are more preferable in using a Scrum model, which means that we have many agile cycles and time-boxed iterations so that we can monitor and quickly adapt to changes. The third step is to decide upon the architectural design, whether this decentralized application will be hosted on a permissionless or a permission network. The business logic, we may need to consider this choice as well, based also on the scalability that we would like to offer to the users. The next step is, of course, the development. This is where the software engineering and the implementation phase takes place. Prototyping the user interface, which, as I mentioned previously, this is the front end. This is what the user will interact to. Then we have the implementation, the development of the backend, which consists of the set of smart contracts. The smart contracts, again, they encapsulate the execution of the business logic. And of course, at the backend also, we have the wallets that are necessary for the interactivity with the blockchain, our interfaces that are required by the platform so that we communicate and send the transactions. So the next step is of course, the internal audit, which is very important. Once we deploy, once we finish with the development, usually deploy the application on a private network that we have already built on our machines or the local host, or we can use one of the many test networks out there. For the case of Ethereum, for example, we have the mainnet, and then we have a choice of testnets that we can deploy our smart contracts and our applications so that we can test it. We can review the code, etc. The same can also be done on the implementation of a private, let's say, protocol on our local machines so that we can do the testings, etc. before we take the application live. And then the last step is of course, the deployment of this application to the mainnet. And usually what happens for visibility, we can also register that decentralized application to one directory of decentralized applications so that people can access our decentralized application. So there are various built-in blocks during the life cycle of decentralized application development. And as I mentioned previously, there are certain considerations and things that we need to ensure here. Various technologies that we can use this is mostly for developers and programmers. Usually the implementation takes place on a JavaScript framework, usually using HTML5 and the classical, let's say, web application technology stack. And then at the back end, we have the smart contracts. For example, we can implement smart contracts on Solidity that are compiled on the Ethereum virtual machine. For storage, again, we need to make a decision here whether we will be taking the data off chain, and this is the most appropriate choice in cases that we have archived data or large pieces of data, or use a totally decentralized peer-to-peer protocol to store our data. And of course, we need the protocol, the decentralized protocol to support all this. For example, we can use Ethereum or any other blockchain protocol, depending again on the business logic and the requirements of the application that we are building. So there are a couple of development steps in order to improve our productivity and write and deploy smart contracts. Usually this development, it happens using an integrated development environment. There are various IDs out there. One popular choice of an ID that runs on the browser is, of course, Remix ID. We can use Remix ID to do rapid prototyping of our smart contracts. We can either deploy them on the testnet, or we can use JavaScript and the embedded JavaScript Ethereum virtual machine so that we can do our rapid prototyping and test with further implementation. For the more traditional programmers, of course, you can use your traditional text editor. However, you will need a compiler in order to compile the Solidity code to the bytecode that is deployed then on the network. Some properties with regards to smart contracts that are offered by distributed ledger platforms is, of course, the guarantee of a deterministic execution. This means that smart contracts are always deterministic. meaning that for the same input, we will always get the same output. And this was why there was, at the beginning of the evolution of such protocols, there was a great discussion whether we should be changing the state of smart contracts by looking at data from the outside world. This is because oracles have also there are risks with regards to the trustworthiness of the information that is passed to the smart contract, but of course this is outside the context of this course. We have isolation, meaning that everything runs on a sandbox environment. And even the state of the smart contract is currently actually isolated within the address of the smart contract. And we have termination, we have some properties with regards to the Turing completeness of the smart contracts, assuming that we are using a protocol that permits for Turing complete execution of code. Bitcoin, for example, with Bitcoin script is not Turing complete. However, the Ethereum virtual machine is considered a Turing complete language, which means that it allows jumps and loops, etc. Some decisions to consider here. First of all, when we design a decentralized application, we need to take into consideration also the financials. As we have currently seen with mainnet at the moment, due to the high congestion of the network with decentralized finance, it is quite expensive to deploy or even interact with a smart contract. So this is another decision that we need to take into consideration when we design our decentralized application. Moving from these considerations to the actual life cycle of implementing a decentralized application or a smart contract, which both of them unfold into the following steps, high-level steps, which is, as I mentioned previously, the development using an IDE, where we are actually using the language, the keyword language, in order to write the code. Then using the compiler, if it is Solidity, then we will use Sol-C, which is the compiler of Solidity, to translate the human readable code to something that is interpretable by the Ethereum virtual machine. And then we do our testing either on a private Ethereum network. And then if we're happy with that, there are no bugs, etc., then we need to deploy it. And at the end, at the last step, we have the maintenance, which is considerations with regards to upgrading our smart contract. This usually happens with the deployment of a new contract and redirecting the function calls to the new contract, etc. So these are in general the life cycle steps for smart contract development. Considerations, as I mentioned previously, we have also the cost that is associated with the deployment of smart contracts. We have also some other considerations to take into account. For example, we have the callbacks in cases that we have a change that is happening at the state of the contract. This is a dynamic event that we need to have some callback functions in order to pick up that change and react. In some of the cases, even some of the arithmetic operations are not fixed, and we've seen in the past several hacks that happen in smart contracts with taking operations. We have some language inconsistencies. You can see, for example, the Pragma compiler that is actually changing day by day. Therefore, we need to make sure that we are using the latest constructs of the language. We need to make sure that we're using the right version. As you probably know, this is blockchains in general are still maturing. The technology is considered as a bleeding edge, which means that there are many inconsistencies also, and we need to set some guidelines and patterns when we design our software. And I'm laying some considerations, some important considerations that one needs to take into account when developing such smart contracts. In most of the cases, lack of best practices is also one of the reasons that we are still finding bugs in smart contracts. One example was recently with decentralized finance. We've seen cases where smart contracts had some vulnerabilities, and we've seen attackers that took advantage of these vulnerabilities to, use the networks for their advantage. Some other considerations for the last part is that we need to take into account speed. Okay, so if we are changing the state on a smart contract, we need to wait for the consensus to take place. Is not an instant transaction. Okay, so that's something that we need to consider also, especially for building real-time, let's say, applications. Transparency of an open source is another thing. We need to take into consideration that the bytecode could be reverse engineered, and this is the philosophy of having transparency of such networks. Interoperability is another dimension that we need to take into account. How do we make a new system interoperable with our current infrastructure and current systems or APIs? Scalability, it's another challenge for us. How can we roll back the effects of or unwitting transaction? This is something also that we need to take into account. This is not, of course, possible, and this goes against this idea and philosophy of immutability. Okay, and usually the compiler that we are currently using is not the most expressive compiler in terms of defining or describing possible errors or bugs, so that we can easily debug it. But overall, the system is maturing, the ecosystem is maturing. There are nowadays many tools out there, open source tools, that can also assist the development process and also the auditing and debugging process. Moving from the theoretical part of topic 3, this part is a bit more technical to the level of, as I mentioned previously, building our own private Ethereum network or a private blockchain in our systems, so that we can interact with it either by creating some accounts and issuing some transactions to the network, or even deploying our contracts. There are various ways to do it. You can either use the Truffle framework, or you can also build your own using the Geth client of Ethereum, for example. In this particular hands-on exercise, I will be using Geth, the open source Go implementation of the Ethereum client. I will be showing you or guiding you through an example on how to build your own private network on your local machines. Of course, the decisions that I made when I was designing this exercise was also to be able to transfer this to any machines, and therefore I'm gonna use Docker containers to do it, and I will have one Docker container representing a different client and different user, and I will also be assigning some privileges to the nodes, to the clients, which so basically setup I will be setting up 4 nodes. So I will be setting up 2 client nodes. The sealer node, which is the miner node, it's necessary for the progression of the chain. Since this is a permission blockchain that I will be building, I will be using the proof of authority algorithm, CLIC, which is mentioned as part of the Ethereum framework, and I will also be setting up a boot node for making sure that my nodes are discoverable by the other nodes. Okay, Perfect. So going through the example quickly. So we have a Docker image that we need to download, and there are some, I'm showing exactly a walkthrough on how you can go about to implement your own. Everything is tested, and therefore you shouldn't have any problems with it. I'm also here showing an abstraction of the network that we will be building. As I mentioned previously, we will have 4 nodes. This particular setup, we have 2 client nodes in different ports, since we are using the same machine to build them. However, you can use this build and set it up in different machines, since we are Dockerizing everything. We have also the sealer node. The sealer node is the actual miner, the node that participates to the proof of authority, the consensus algorithm. In this case, signing transactions, assigning blocks and generating blocks and assigning them for the continuation of the blockchain. And then we have the boot nodes that everyone utilizes in order to do our discovery for our private implementation. Usually, if you are not setting up the boot nodes, then you are running the risk at connecting with the mainnet. So having the boot node restricts this or isolates nodes to the current environment, and therefore this is the preferable way to do it, to set it up. So moving from there, just showing how we can instantiate our Docker containers. Since we have downloaded the image, everything is open source, by the way. You can use it. You can just follow the instructions, the walkthrough, and at the end of it, without any problems, you will be able to run your own private Ethereum network and interact with it. So Docker run, some prerequisites. You need to install on your machines Docker and Docker Composer. That's the only prerequisite required for this exercise. So Docker run is with Docker run we can instantiate our Docker image into a container. Therefore, in this case, I'm setting up the client. You can also use the Docker PS command in order to make sure that everything was instantiated. Have already done this exercise and you would like to resume, you don't have to run Docker run again. You don't have to repeat it, since Docker run instantiates the same object and creates a new object, and therefore we don't need that. You can just stop and start your Docker container if you are resuming this exercise. So once we set up our containers, we make them interactive. That means that we can access that command line. We can, from there, call the get client. And in this particular steps, I'm showing how you can call the get client and build some accounts. So just to make clear here, each client in a blockchain network is identifiable by a pair of keys. This is the account that we are mentioning here. Therefore, we are just in identities here for each node, meaning that each node is identified by at least one public key and a private key. Okay. With Get, you can create multiple accounts using the same private key. So we have, as I mentioned previously, we are building identities. We have 3 nodes and nodes. So these are the 3 nodes that we have identities for, with only exception the boot nodes. This is how the network looks at the moment. We haven't done any setup. We haven't assigned any roles. Okay. So this is since we are building a private Ethereum network here, we are also able to set some roles. Okay. So as I mentioned previously at the beginning of this exercise, one of these nodes will be acting as the authority. Okay. You can have multiple nodes acting as the authority. However, in this example, we are just focusing on one. However, you can follow the same steps for adding more authority nodes, etc., and more clients, of course. So at this stage, we will need to create the genesis. So it's we need to create the network, because at the moment we have 3 ad hoc containers. Nobody knows no one, and the nodes are not communicating with each other. Okay, so our aim here is to create the genesis of this blockchain. Okay, and at the same time, we will also be setting up the connections between the nodes. So it's a peer-to-peer network, so we will set it up. So one of the nodes, the responsibility for implementing the Genesis file. We call it the Genesis file is just a JSON file that indicates the parameters for our network, such as, for example, the name of the network, how many coins to mint it, the details with regards to the network setup, the accounts to be refunded, the sealers, the miners, the authorities, etc. So we need to set up the Genesis file, this JSON file, and in order to do that, we're not going to do it manually. There is a tool that we can use, an interactive tool. This tool is called Puppet. We're going to use that tool in order to create the Genesis file, the JSON. So we're just following up on-screen instructions. We set up the sealer account, and we also define some accounts to be pre-funded. This is advisable, at least for the sealer node, because we will need some gas at the beginning in order to sign the first block. So we need to pay the gas, and also from the Genesis file, we can set up the difficulty of this network, etc. All the parameters that are used to set up the network. Once we do that, once we have the Genesis file, we need to copy that to all other nodes that will be participating to our network. This is necessary since we need to let the other nodes know of the properties of this network that they will be participating on. Okay, so this is something necessary, and I'm showing here a couple of commands that you can use to copy it on your Docker container. So since we are using Docker containers, we need to pass this Genesis file to all containers, etc. So following from there, we need to initialize our network. So one of the nodes, so all the nodes need to execute this command. Okay, so we initialize it, and we're making sure that we are connecting to the right network. Okay, so the walkthrough shows all the instructions in order to initialize all Docker containers. However, as you will be noticing at this stage, the nodes, the peers, are actually kind of idle since they cannot see their other peers. This will be the responsibility of the boot node. We haven't discussed the boot node yet. However, we need to build the boot nodes so that it handles the discovery of the other peers within our network. Okay, so in order to initialize the boot node, we have 4 containers at the beginning. So one of these containers will act as the boot node. Usually, boot nodes are static IP nodes, meaning that they should be easily discoverable by the peers, so that they can find the network, the other peers that are participating to the same network. So these steps are indicating how the boot node is setting up. Again, here are some instructions that you need to follow. Since we are building Docker containers, we are on the same machine, we need to be behind the NAT, and therefore we need to make some certain configurations here for our nodes to be discoverable. So once we do that, we can start the clients with the following command. Once we start the clients, then we will see the boot nodes, their activity on our boot nodes. And once we initialize all clients from the Docker containers, at the end, we will see the interaction between all the nodes. And the next step is to make the network progress to the next block. Since we haven't initiated the authority account, we need to have at least one miner mining, in this case, generating and signing blocks. So we need to start and this is how we start the sealer account on the network. Once we run the sealer account, you will then be able to see that our network is reacting chain. That is now an that evolves and continues to be built. Okay, so we will see a continuation of new blocks mined and registered, etc., and appended on our ledger. Okay, so we can also generate transactions. We can also create accounts, and I'm just showing here a couple of commands on how we can interact now using the get JavaScript command line. That's all. Any questions at this point? That's the end of this session. Any questions? Thank you all. I hope that you find it fruitful. If there are no questions, we can proceed with the rest of the material for today.
Thank you, Clayton. Actually, I will be proceeding with section 4. We will be discussing, of course, some use cases now. Valentino, the token for sharing the screen, please. Okay, let me just go to full view. Okay. All right, can everybody see the screen now? Great. Well, okay, thank you both, Clayton and Ilya, for presenting the previous sections. So we're moving now to some use cases, briefly discuss them on decentralized applications. We will look at decentralized exchange markets, the data markets, the blockchain verifiable certificates, and discuss a little bit self-sovereign identities, and discuss at the end some new emerging topics within the broader framework of decentralized applications. Well, we don't need this now. All right, so decentralized exchange markets. If we look at actually what is a decentralized market, going back to the definition of DLTs and blockchain in itself, in a decentralized market, blockchain technology enables the various participating parties to deal directly with each other instead of operating from within a centralized exchange. So virtual markets that use decentralized currencies or cryptocurrencies, as we refer to them, are examples basically of decentralized markets. Looking directly at an exchange, the various components in an exchange, we see that the various components is the buyers, the sellers, the financial instruments that we have, like the currency, commodities, the quantity in trade, and the price of the financial instruments against another one. So let's continue. With the advent of technologies, we have created many opportunities for that. So a decentralized market, as we said, it enables the various participants to interact with each other. Advantages, of course, we can look at them, are the advantages that we have when it comes to blockchain technologies and DLTs, like transparency, lower transaction costs due to the absence of the intermediaries, increased security, and of course, freedom. So let me see, there is some question I see here. Wait a minute. I cannot see my comments here. Let me, okay, let me just quickly escape from, Valentino, I cannot read the comments. Can you read them?
Yes, I can try closing the Q&A.
I should
Minimize it.
You don't see my screen? Let me see.
We see part of it.
Oh, I'm sorry. Okay. And how about now? Better?
Yeah, a little better.
What did I do wrong? Like, give me a second, please, and see what is happening. Shall I try again? Wait a minute. Okay, I will stop sharing and try it again. Close this, maybe. All of this. Okay, let's try again. Sorry about that. I think I was, where was I now? The presentation was this one. How about now?
We are seeing the second screen.
You're seeing the second screen. Oh, how did I manage to do that? Okay, let me. Okay, my mouse is not working. Swap. How about now?
Yes.
Actually, this is what I was trying to do earlier, and I wasn't able to. And now I did it by accident. Okay, so let's continue. All right, here we see some examples of decentralized exchange markets that already exist, from Uniswap to Care Finance. So actually, there are quite a few around. So we're not going to go into them. What we see here actually in this figure is the top 10 decentralized exchanges according to the volume of exchange that they have. Okay. And another example for Uniswap. All right, we can skip that. Now, Let's move now to the second use case that we have on decentralized data markets. In a decentralized system, all the data is actually, they form a unified body that is stored on one computer, as we know. Now, to get the information we need to connect to the main computer that we refer to it as a server. In terms of when we are talking about decentralized data markets, it means that, again, that there is no central storage. And some servers provide the information to the clients. The reason that we prefer doing that is because of the better security that they provide. Klidos has already mentioned IPFS to us, which is again an example of decentralized storage. Besides that, we have Filecoin, SIAM, Storage, Swarm, and quite a few others as well. A little bit more on IP. Websites, applications, and data. It allows users to store and transfer the verifiable data with each other, and our data is actually hosted by the various nodes pinning to the desired data that we need. And of course, IPFS supports blockchains, and it offers immutable permanent links to transactions, timestamping, security, secure content. Again, the various characteristics that we know of blockchain technologies. We're not going to go for now, as we're just giving the highlights of how IPFS works. And we'll move to, and the other example is Filecoin again. And in terms of the common features that Filecoin and IPFS have, is the fact that the IPLD, they both use blockchain data structures. And the Filecoin nodes, they establish secure connections with each other. Okay. Another interesting one is actually SIA, which is used again to leverage blockchain technology to create a data storage marketplace that is more robust and affordable. Looking at the various literature that exists, they say that SIA is actually more robust than the rest that we have at this point in time. Maybe it's just advertising. Now, this is a map that shows the various SIA providers around the world. So storage capacity of 2 petabytes, providers 318, and the downloads. Now, when it comes to blockchain verifiable certificates, I believe you're all aware that at the University of Nicosia, we started doing this back in 2015, actually, starting to issuing certificates on the blockchain. And the use case that we are presenting here is actually our own. We know that in terms of, when it comes, for example, to academic certificates, academic diplomas, or any other kind of certificates that exist, it's easy faking them or losing them. It's very easy. And we require a lot of paperwork. it is recorded that 2 trillion something data records are stolen every year. So one can imagine the problems that we face because of this. So at the university, what we actually did here, I'm sorry, we took the PDF file of the certificate, and within that PDF, let me just find the correct slide here. All right. Within that PDF, we inserted some metadata such as, for example, the name of the student, the program the student is studying, and some other details in regards to that. And then we, instead of uploading on the blockchain one certificate at a time, let's say that for a certain academic year, we have 1,000 graduates, then those 1,000 certificates that we have with the metadata will form a Merkle tree, and the root of the Merkle tree will be uploaded on the blockchain. And of course, the student who wants to go into find some job, they can send the PDF that they have in their hands to the prospect employer, so that the prospect employer can actually upload the certificate that he or she has on our validator, and identify whether that certificate is valid or not. We're collaborating with several universities around the globe for doing this, and companies for different types of certificates. Also, many times students may come and say that my name is spelled wrong on a certificate. So what we can do is we can revoke a specific record and reissue it again, so that the student has the correct certificate, the correct data on his or her certificate. Sorry, let me back up a little bit again to go into self-sovereignty. Users usually identify themselves by their with the certificates that they have. Users may identify themselves, and at the same time they maintain control and of their credentials. This is exactly what self-sovereignty is about. So within that, the case that we have at the university, we can say that we can apply also self-sovereignty through the certificates that we're using. Some more on emerging topics. Of course, we know that blockchain technologies, DLTs, they can be applied in a variety of industries, ranging from analytics to governance to supply chains. For privacy security, we have a lot of work being done towards that area, and more applications are being built and use cases continuously. Of course, we have at this point in time quite some adoption issues, but we believe that eventually these technologies, the power of these technologies will be realized by industries. The costs, as we have mentioned in the before, could be relatively high. So this is also one of the constraints that keeps the various organizations behind from actually going into the implementation. And that's it for me on use cases. And I will, if there are any questions. I can take them. Just a second. Stop sharing. All right. Chat. Okay. All right. Any questions from anybody? I don't see anything. Okay, then, Ilya, the floor is yours again. Let me stop the video. Okay.
Okay.
Αρχικά αυτό στο POS.
Sorry. Sure. Can you see my screen now? Okay. I assume that you can see my screen now. Is
Yes,
sharing
yes, we can see your
properly.
screen.
So the fifth and final topic for learning module number 7 for this module is to have an overview about the relation of decentralized applications and the concept of the fourth industrial revolution. Let me say from the very beginning that both terms, especially the second one, I refer to the term of dApps and of course to the term of fourth industrial revolution are quite broad. So many things can be categorized under the semantic scope of this terminology, especially under the scope of fourth industrial revolution. Our purpose here is not to have an exhaustive analysis of what can be studied, explored in this context. This is almost impossible for a single learning module, even for a series of modules. Our intention is to give you the right direction for your study. One of the things that can be fairly categorized as lying on the overlap of dApps and fourth industrial revolution is the relation between emerging technologies like IoT, blockchain, and artificial intelligence. By saying relation, I'm referring to their convergence, and see what is how this is possible and what means in practice. So let me start by asking a very quick question to see your views. Almost every day we are reading things like IoT, AI, blockchain can work together, and something really big is expected for the immediate future. Other types of such discussions include the top demanding jobs in the industry, especially digital industry, etc. Why do you believe we are seeing such strong statements? Why do you believe such strong expectations are being developed in the technology sector? Do you see a natural fit between those emerging technologies? Asking this very specific question to set up the context of your understanding, meaning the scope that has been created, and see how we can put some things on the correct basis. So, any ideas, any views, comments about why bringing these three different things together? Do you believe that it is a good idea to develop skills across these three disciplines? Do you find this um, useful investing time in learning blockchain technology, also learning the relation of AI and IoT with regards to blockchain? Do you find exciting this array of disciplines? Let's start from this very basic question. So while we are waiting for your comments, views, my personal opinion is, yes, indeed, is quite I think it's replying to, first of all, now I'm seeing the question. Replying to Ben's comment, all these three are being developed, are being evolving independently. So also well beyond data only. This is it's not the understanding and the analysis of the opportunities and challenges does not always require a deep technical knowledge. It depends how things are being presented, and just because this is let us remind ourselves that this series of events, these lectures are conducted within the context of the DLT4ALL European Erasmus Plus projects, and the idea is to put the right foundations regarding blockchain technologies from a clear learning perspective. So this is related to the last comment about whether technical knowledge is required or not. As an instructor, as a teacher, as a faculty member at the University of Nicosia, I strongly believe that even the most technical topic, let's say, has some angles from which can be approached and delivered to a non-technical audience. And this has to do primarily with two things, with the teacher as well as with the material used. Let me say that one of the motivations of, as mentioned by by Professor Luca earlier in this session, the lack of the appropriate material and the fact that the knowledge is fragmented creates some misunderstandings about how such types of technologies work, both separately as well as together. So,
Ilya, may I interrupt for a second?
yeah.
Yeah, well, I mean, thank you for pointing this part regarding thing. As Elias has already mentioned, all these different modules may contain both technical and non-technical material, as we are targeting a variety of groups. What the consortium has decided to do is material that our audience finds more technical to label them as technical material. So this will enable them, if they don't want to follow the specific slides, to just skip to the next one, which is more business oriented, let's say. So this is the approach that we are aiming to have. So we would greatly appreciate it if parts that you thought they were too technical, to point them out to us also in your feedback, please. So thank you, Leah. This is all I wanted to say for now.
So Sula, this is very, very I mean, practically speaking, interesting. And I would say the following. Yes, this is, I think, one of the great features of DLT4ALL project, that we are covering a wide spectrum of audience, and our approach is carefully designed, and such events gives us the opportunity to receive useful constructive feedback. However, in addition, I would say that there are always ways to approach even the most technically demanding or the most demanding topic from certain angles. And towards the end of this part, I will very quickly demonstrate a way. That is, I will rule out complex equations, buzzwords, terminology, and things, and demonstrate very quickly how AI, well-tested AI, no need to refer to deep neural things, etc. Well-tested AI models can be used by the average, let's say, learner who has an average degree of familiarity with the use of GUI-based tools. But let's save this towards the end. So this is pretty much the idea. I know that IoT, blockchain, AI are some strong words, terms you hear every day. So feel free to interrupt me and ask me specific questions. The idea of this part, as well as the idea of this learning module, as well as the idea of the entire DLT4ALL project, is to focus on the fundamental principles and demystify some vague things. So I will try to focus on the interesting and the key things. So often we hear that we are approaching the fourth industrial revolution. This is a nice label. This is a characterization of the industrial age. I would say that to keep things simple and solid, Yes, we are witnessing a technological revolution. We are seeing an increment of productivity. Fourth industrial revolution is it's a term. It's very difficult to set accurately the boundaries between the X and Y and I don't know, phases of the revolution. However, the main message here is that we have the utilization of different digital technologies. Different means we need to make these technologies work together. This is the interoperability challenge, as mentioned by my colleague Klitos. And this integration changes the traditional processes and how business was conducted. So we have a transformation. This is pretty much the notion of the fourth industrial revolution. You may add few properties more, but however, this is more or less. So in relation to that, often we hear about the singularity, say, aspect of this. Singularity has to do with the so-called superintelligence that may result into some AI-based systems that may exceed the human level of intelligence with unknown results. Okay, this is a huge debate, huge discussion. I think it's not something that you know, will ever be solved or handled more or less in a way that the society will consider these challenges trivial. Always we have to critically think and review the impact of the technology to the society. I think from my perspective, this is the key thing here. So many different types of digital technologies can be categorized under the fourth industrial era, including mobile computing, IoT, 3D printing, blockchain, of course, AI, etc., etc. So, in other words, any emerging technology with high expected impact on our lives can be easily listed under such compilations of technologies. So this is just a list. Any questions about how we define the fourth industrial revolution? What it means to us? Why do we very frequently hear this term, etc.? Any questions about what is meant by the fourth industrial revolution? Why this is so important? I guess that we are okay, and let's start seeing what things mean. So, starting from the Internet of Things, the key idea here is that IoT can be defined as a set of interconnected devices that have hardware and software which enable those devices to consume and produce data. Those devices include smartphones, laptops, desktops, smart other smart devices used in a daily basis, etc., and everything in between, or everything being similar to those devices. The numbers here are impressive. We are at the billion magnitude. This is happening both at the consumer and at the enterprise level. So is as different implementations of the generic IoT paradigm can be found at the consumer as well as at the enterprise level. Now, AI. Replying to, we have a comment about the definition of fourth industrial revolution, suggesting that seamless integration between man and enterprise West. This is quite correct. This is a nice generic definition, which is, I think, holds for many things, including fourth industrial revolution. Yeah, the scalability is among the problems that those technologies are trying to solve, and this is a response to a comment suggesting that the high frequency of upgrades and versioning of hardware and software is a real challenge about the integration. Of course, this challenge also holds also at the individual level. I mean, when we consider the constituent technologies at their own level. So let us see what we mean by the term AI. It's a field of computer science and engineering, which focuses on the design and development of intelligent systems. And those systems are supposed to perform tasks that require certain degrees of intelligence. And when we are reaching a point where such systems outperform human intelligence, and then things become very interesting. Overall, we can say that the AI interacts with the environment, and this interaction more or less dictates the need for processing signals and information coming from at least three basic modalities, in which are the audio / speech modality, the image / video modality, and the written language. Now, difference between AI and machine learning. So, any ideas? I think the answer is here. Machine learning is a special field of AI, where the learning capabilities of the system are based on past experience, and this past experience is encoded on data used for training. That's why there is the saying suggesting that data is the new oil, because such data are used as the gas, as the oil for training such system overall. And this is quite important to know at a generic level. We have two types of problems we are solving in the area of machine learning. We have the regression and classification problem. No, it's machine learning. It's AI. It's the broader field, including many approaches like top down, bottom up, etc. Machine learning is the data driven approach. So the main steps for this is to collect data, extract the features, apply and training for the algorithms, do some fine tuning, and finally test the systems. So now, what's the relation between the three technologies? I mean, three types of technologies: IoT, AI, and blockchain. I think this pyramid here gives a very nice depiction of the relation. So imagine IoT providing data that are produced and consumed by interconnected devices like our smartphones. Then at the middle layer, we have intelligent algorithms that can be trained from those data. And the services that are enabled through those smart algorithms can be provided through smart contracts coupled with native cryptocurrencies, which of course are possible when we are using a blockchain-based system. So this is the overall connection between the three types of technologies. In summary, IoT generates data, AI consumes those data for training intelligent models, and blockchain utilizes those models for building decentralized applications and having also a tokenization scheme through the native tokens. I will skip those details because we are providing the references to research papers regarding those two use cases. The first use case is the identification of transacting entities using machine learning. This is a research work conducted by colleagues here at the University of Nicosia, specifically Professor Luka, Professor Christodoulou, myself. Also, this is a second work also conducted at our university, the use of business intelligence taking the form of unsupervised learning for automatically algorithmically computing blockchain readiness index. And some quick reference about some related tools. The first one is the Weka machine learning tool. This is an ideal for entry-level users. Once you have the data, you can quickly do very quickly some introductory experiments with those data, incorporating well-tested machine learning algorithms without the need to write complex code and understand complex mathematical configurations. Of course, let me say that the understanding of the foundations is always the best path to fully digest and understand what is under the hood. However, this is well beyond this session, this learning module, and it's beyond the DLT4ALL collection of learning modules. We are just giving here the direction. I have here a set of slides, but I think more useful to see how this thing works live I'm going to do a live demonstration rather than going through the slides. So let me try to minimize thing and find, okay. So you can, this tool is freely available. So you can easily, let's say, having collected a set of data, saying that the data is the new oil, based on this assumption, okay, you can have this data collected in a CSV format similar to Excel. You can inspect the distribution of the data. Also, you can do some pre-processing, that is normalization of the data. I'm not going to show how the pre-processing is done. What is important here is that through few clicks, like for example, choosing this CSV file, this Excel file, okay, we're importing it. Here are the different types of data. Here we have some basic statistics, and here a representation of the distribution of the data and the classification. Actually, this panel right here gives us access to numerous machine learning models. For this demonstration, we may choose SMO, which is the most widely used implementation of support vector machines. Here you can see the parameters. Okay, it's beyond the scope of this session to describe the parameters, but you can configure them. And the test options provide some basic features about the evaluation of this model. Cross validation, tenfold cross validation, is the more frequently used one. We may use that, and you can see that in few seconds this model was evaluated, and that's it, meaning that in less than 3 minutes, given that we have the data, we are in a position to test the application of a machine learning model. This gives us a performance equal to 66%. For comparison purposes, we may choose a different model. We may go for naive Bayes for this particular problem, which gives slightly lower performance, equal to 64. That's it. I mean, so quite easy. So the summary here is that the Weka tool is ideal for for users that would like to have a very quick and basic understanding of hands-on experiments with real data. Okay, in the next screenshots, we can see what we have seen live. And the last part is about Web3 PI. Is actually a Python implementation of what was presented at some parts of Clito's presentation earlier. And the idea here is to have a way to connect to smart contracts through the Python environment, and I will explain how this is done. So we are providing a few examples about how this can be done using the Infura endpoint, which enables us to connect to various Ethereum networks. So this script checks the connectivity. The next one retrieves some basic block information, checking the balance of an address. Here things become more interesting because having deployed a smart contract, we can access the function of this smart contract. Specifically here, we can check the total supply of a token. And regarding the integration of all those technologies, this is a summary of the required steps. First of all, you need to identify the appropriate machine learning model. Then you can transfer this model to Python. Then augment the previous step using by putting in some hooks for Web3 PI, and this explains why I suggest the use of Python regarding the integration of machine learning and blockchain, because an excellent library of machine learning models in Python is the scikit-learn library. So within the same language, Python, you can have two different libraries dealing with machine learning and smart contracts. So it's a natural way to bring these two technologies together through Python. And of course, the use of data processing libraries like Pandas is a nice tool for monitoring your application. And having such integration in place, you can start thinking of examples of fourth industrial revolution, where even machine-to-machine interactions can be implemented. And the main conclusion is be ready for changes. Those changes will have impact, and the safest way to be prepared is through learning, which is of course the cornerstone of the DLT4ALL project. And we conclude this part with the usual set of multiple choice questions, as well as some basic and optional references. Here under the optional references, you can see our research work that we are previously used as use cases, the identity discovery in Bitcoin blockchain, and our algorithmic approach for computing and blockchain readiness index. So, thank you.
Okay, thank you, Ilya and Glidon. Are there any questions from our audience? Well, then this brings us to the end of this today's seminar. Please join us tomorrow also for distributed autonomous systems. As I have mentioned earlier, all the different slides from all the modules that we have within the project will be uploaded in an instance of Moodle, and we will be sending you further information on how to access them. In addition to that, the videos will also be uploaded on our YouTube channel and on the website of DLT. In addition to that, we will be sending out a questionnaire. Please fill it for us. Your feedback will help us improve this content. So thank you again all for attending this seminar. See you all tomorrow. Bye, everybody. Have a nice day.